Here's the lecture notes for section 9.4, radius of convergence. We're going to cover a lot in this particular section. I'm going to go through minimal um, samples. What really needs to be done is you need to do lots and lots of practice problems to get the ideas down. Idea number one is the idea that there's this thing called a radius of convergence. That is, whenever we have a power series, there's only three possibilities for the convergence of that power series. Um, Possibility number one is that there is some positive number r. And if we go from the center up r and go from the center down r, we create a rough interval. And that's where the convergence is. If it's not convergent out here, then it's not convergent on the other side. There's an equal amount, which is one of the reasons why we call A the center of the power series. Another possibility is that you go out from A infinitely. And that is to say that the series actually converges for all the values of X. And the last one is that it converges at A. In other words, the radius convergence is zero. You can't move for there. A is the only place that it does converge. So that's idea number one. Power series have radius of convergence. All right. Item number two. This is something that we talked about earlier, and that is the nth term test. A reminder that if we encounter a series and the limit of the nth term is anything but zero, then we say the series diverges. So for some series, it's really, really handy. It says, hey, take a look at this series. I'm going to do a quick check. The limit as n approaches infinity of n over n plus 1 is equal to 1, and 1 does not equal 0. Therefore, this series diverges. And that's the whole thing. Now, the thing that we need to watch out for as we talk about this second idea is that you can't use the nth term test to show convergence, only for divergence. So even though the limit as n approaches infinity of 1 over n is equal to 0, this does not prove convergence. All right, that's that. Nothing more to be said. Can't use the nth-term test to show convergence. Next thing on our list, we introduced the idea of absolute convergence. And that is, if we have an infinite series and we make every single term in that series positive, or at least non-negative, and it converges. So in other words, the series made up of only positive number converges, then we call that series a absolutely convergent series, or we say that that series converges absolutely. Why would we want to say that? Well, it just so happens that if you can get a series to, if you can say that the series converges absolutely, then we know the series, even if it has negative values or a combination of positive and negative values in it, it will also converge. It's much harder to have a series converge made up of only positive terms than it is to have one made up of a combination of positives and negatives. Another way to look at this is that if we had a set of all series, then we can break those set down into the convergent and divergent series. A subset of convergent series are absolutely convergent. If I'm in this subset, I am also in the set of convergent series. If a series converges absolutely, then it also converges. There's the big takeaway there. Okay, well, next big idea coming up, and that is ratio test. It says, let the series A sub n be made up of only positive terms. And let's say we find the limit of the n plus 1 term to the nth term, and it's equal to some value L. If the value of L is less than 1, the series converges. If the value of L is greater than 1, then the series diverges. If the value of L is equal to 1, this test doesn't tell us anything. Now, let's talk about why we needed the thing above as we talk about ratio tests. What we often do when we do the ratio test is we end up really taking the limit as n goes to infinity of the absolute value of n plus 1 and the absolute value of n. And in doing so, we are now looking at the absolute series and we're finding absolute convergence. And then we can do and find the L and so on and so forth. So we think of, in general, when we throw these absolute value symbols around there, that the ratio test is actually a test of absolute convergence. All right, now let's apply the ratio test to a simple example. And that is, hey, what about f of x is equal to e to the x? That is 1 plus x squared over 2 factorial, x cubed over 3 factorial, or in general, x to the nth over n factorial. Can we find out can we show that it converges for all values x? Well, if I take the limit as n goes to infinity, and out of habit, I'm just going to put those absolute value symbols on there. And I put the n plus 1 term. In other words, every place I see an n, I replace it with n plus 1. And I divide it by the nth term. Now, this is awkwardly written, so I'm going to rewrite this as the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. Now, I'm going to do one last rewrite so it makes it clear how we're looking at this. X to the n plus 1 over x to the nth. N factorial over n plus 1 factorial. Now, if I simplify this expression, I get simply just x. There's one more x up top than there is on bottom in terms of multipliers. When I look at this expression, I get 1 over n because the top expression is n times n minus 1 times n minus 2, etc. The bottom expression is n plus 1 times n minus 1 times n minus 2, etc. All of these terms cancel with all of these terms, leaving only the n minus 1. Now, for any finite value x, I've got a finite value x divided by an infinite value n plus 1. That's equal to 0. That's our value of L, and that value of L is less than 1. Therefore, this series, x to the nth over n factorial, then goes from 0 to infinity, converges by the ratio test. Let's see if we can use the ratio test to find the radius of convergence for this particular series. Again, I will start by saying the limit as n goes to infinity of n plus 1, x to the n plus 1 over 10 to the n plus 1, and I'll multiply by the reciprocal 10 to the nth and x to the nth. And if I rewrite this I can think of this as n plus 1 over n. I can think of this as x to the n plus 1 over x to the nth. And I can think of this as 10 to the nth over 10 to the n plus 1. Simplifying this expression, I can't do anything with n plus 1 and n. There's no cancellation there. But I do get an x here, and I do get a 1 divided by 10 there. When I apply the limit, as n goes to infinity, this expression is going to go to 1, leaving me just the absolute value of x over 10. And so now I ask the question, well, when is that expression less than 1? When is the absolute value of x over 10 less than 1? Well, it's when x over 10 is between -1 and 1. Multiplying each section by 10, I find that if I go from the center up and down, the center being 0, I've got a radius of convergence of 10. Let's take a look at this next one. Again, we'll use ratio tests. Talk about the limit as n goes to infinity of the absolute value of n plus 1 factorial x to the n plus 1. And in this one, I can write n factorial and x to the nth. And when I do my cancellations this time, I get n plus 1 when these two cancel, and I get x. Now, when n goes to infinity, for every single non-zero value of x, well, actually, let me write this out. If x does not equal to 0, then the limit as n goes to infinity of n plus 1 times x is equal to infinity. And by the way, infinity is greater than 1, which means it diverges. But if x is equal to 0, then I've got the limit as n goes to infinity of n plus 1 times 0, which is equal to 0, which is less than 1, and that's convergent. So this is one of those situations where this particular series converges, but only for x equals 0, or in other words, the radius of convergence is 0. It doesn't move away from the center. All right, let's take a ratio test one more for this one. And that is, what do we get? The limit as n approaches infinity of absolute value 3n plus 1 over 5n plus 1 plus 1 multiplied by the reciprocal 5n plus 1 over 3n. All right. Limit as n goes to infinity. And this one, well, let's take 3n plus 1 over 3n. Well, I know what's going to go happen there. How about 5n plus 1 over 5n plus 1 plus 1? All right. I think maybe it's pretty clear to see that that's going to reduce to 3. Is it clear that that is going to end up being 1/5? That when n gets really, really big, the plus 1 that's there and there are going to be not very meaningful, and we get a 1/5? If so, we have a limit of 3/5, which is less than 1. Therefore, the series converges by the ratio test. By the way, if it's not clear, let's just do a little side work here. A little side work. If it's not clear that this goes to 1/5. Perhaps we could recognize that this is indeterminate in the form of infinity over infinity, and therefore L'Hopital's rule applies. And you get the limit as n goes to infinity of 5 to the nth times natural log of 5, and we get 5 to the n plus 1 times the natural log of 5. Those cancel, and that clearly goes to 1/5. So just in case you can't see that. All right. So we've handled a definition of radius of convergence and term test for divergence, absolute convergence, and the ratio test. Leaves us with one last problem, which is none of the previous things that we talked about. This particular series is called a telescoping series. And it uses partial fraction decomposition in order to see how it actually converges or not. Let me talk you through it. Let's do a little side work and note that 1 over n times n plus 1 is equivalent to a over n plus b over n plus 1. Or 1 is equal to a times n plus 1 plus b times n. If we set n equal to 0, we get 1 is equal to a. If we set n equal to -1, we get 1 is equal to, this becomes a 0, and we get negative b, or in other words, b is -1. In other words, this expression is equal to a over n minus 1 over n plus 1. Now, the reason why that's important is that we can start looking at the partial sums in order to try to determine what's going on with this series. The first partial sum, the sum where n is equal to 1, is 1 minus 1/2. Okay, well, that's not too exciting. Let's take a look at the second partial sum. It's 1 minus 1/2 plus the term what happens when n is 2, which ends up being plus 1/2 minus 1/3. Well, take a look. Oh, those cancel. What about the third partial sum? That'd be 1 minus 1/3, the thing that remains from the second partial sum, plus, and now n is equal to 3, plus 3 minus 4. Wait, now those two terms cancel. Maybe at this point, we can see that the nth partial sum is going to end up being 1 minus 1 over n. And because the sum of an infinite series is the limit as n goes to infinity of the nth partial sum, and now we're saying, well, what is the limit as n goes to infinity of 1 minus 1 over n? Well, that's equal to 1. So this series converges to 1. Our conclusion is that the series from 1 to infinity of 1 over n, n plus 1, is equal to 1. And that concludes the lecture. Lots of stuff. Practice lots of problems, please.